Alright, let's get started. Maybe some more people will join us, maybe they won't. It's Monday before a holiday, so small group today, but that's totally cool. So today we're going to finish up with chapter 12, and we'll get through probably all of chapter 13 today. So that means next week we're going to be doing chapter 14, 15, and 16, so be ready next week. Watch those videos if you have time this weekend, or please watch the videos this weekend so that we can all get back together for next Monday. Because we have not too many weeks left and several more chapters to finish up. So like I mentioned last time, the last few weeks are going to go fast. So for now, let's start by finishing up with chapter 12, which is about control of enzyme activity. So first, we will just start by defining some important terms that we learned about enzyme activity. So can anybody tell me what kind of reaction that is catalyzed by a kinase? Yeah, and what is that process called? There's like a term for it. Yeah, phosphorylation. And phosphorylation, like you just said, is transferring a phosphate group from ATP to the substrate. So what about phosphatases? What kind of reaction do they catalyze? Yeah, dephosphorylation. Not a trick question. And what is dephosphorylation? What does that mean? Yeah. Do you know what process is removing it? Or like what type of reaction it is? Yeah, hydrolysis, exactly. Okay, so that brings us to phosphorylases. What kind of reaction do they catalyze? So that's what kinases do. They do phosphorylation. Phosphorylases, I know they have the word phosphoryl in there, so you'd think they would do phosphorylation, but they don't, which is why we're going over this. Yeah, phosphorylasis. So what does that reaction actually do? Celia? Yeah, you're cleaving a bond. What are you using to help cleave the bond? Yeah, exactly. So you're breaking a bond in the substrate using a free phosphate as the attacking group. So these three reactions, the names, well, not all the names, some of the names sound very similar, the actual reaction names do sound very similar. The enzyme names, some of them sound very similar. So this is why we have this sort of summary to help you all remember which one is which. So phosphorylation is catalyzed by kinases. This is using ATP as a source of phosphate. This is different from a phosphorylase. That type of reaction that's catalyzed by a phosphorylase is not phosphorylation, it's phosphorylasis. And it's using free phosphate as an attacking group, and we're breaking a bond, not making a bond. And phosphatases are also breaking a bond. We're removing a phosphate group by hydrolysis. So hopefully you will all remember that, because we're going to be talking about enzymes that do all these different things. So if you don't understand what they're doing, it will make all the material really confusing. So yeah, so that's why we need to know this. So that brings us to an enzyme called glycogen phosphorylase. So we just talked about in the last slide, phosphorylases catalyze breaking a bond using a phosphate as an attacking group. That's what glycogen phosphorylase does. It removes one glucose molecule at a time from glycogen using phosphate as an attacking group. So the product of this cleavage is my next question for you. So what is the reaction that's catalyzed by glycogen phosphorylase? Yeah. Yeah, exactly. So we have glycogen with N subunits plus inorganic phosphate yields glycogen missing one subunit plus glucose 1-phosphate, which you can write as G1P, So what type of bond is being broken here in our glycogen molecule? Yeah. Yeah. All right, so the next part of this slide is about different ways that this enzyme, glycogen phosphorylase, can be controlled. So there's covalent modification. Does anybody know which covalent modification we're talking about here? Yeah, it is phosphorylation. So not only does this enzyme catalyze a reaction using phosphate groups, it also is controlled by phosphate groups. There are also enzymes that help modify glycogen phosphorylase to do the covalent modification. And then there are also allosteric effectors of glycogen phosphorylase that will affect whether it's in the R form or the T form. So everybody take a few minutes and start filling in this table, and then we can all go over it together in a few minutes. I also want to add, if you are working on this like from the slide deck, there's a slide on the next page that might help you answer the questions in this table. Okay, so let's start filling in this table. So we just mentioned that our covalent modification is phosphorylation. So is phosphorylation going to increase or decrease activity of our enzyme? Yeah, yeah. So phosphorylation, which is the A form. So what modification will decrease the activity of our enzyme? Yeah, dephosphorylation. And we can see that if we look at our little picture diagram. So the phosphorylase A, the phosphorylated form, is shown on the right side of the slide, and the equilibrium is shifted down towards the more active form. For phosphorylase B, this is the dephosphorylated form of our enzyme, and the equilibrium is shifted up towards the inactive form. So yeah, so that brings us to modifying enzymes. What enzymes are going to phosphorylate and dephosphorylate our glycogen phosphorylase enzyme? Yeah, so does the kinase increase or decrease activity? Yeah. So we have phosphorylase kinase, which adds a phosphate group. It actually has two phosphate groups. So what enzyme is going to decrease activity? Go for it. Which one? Yeah, which phosphatase? What did you say? Sorry. Yeah, it's actually phosphoprotein phosphatase. So it's not specific to glycogen phosphorylase. It's a more general protein phosphatase, so it's just called phosphoprotein phosphatase. And yeah, I know these names are all kind of awful and they all sound very similar to each other. So this is why we went over those different reaction types before, and hopefully this will help you understand what all these things mean. What they do is in their name. It's just a matter of remembering what all the names actually mean. And the short name for this phosphoprotein phosphatase, it is often just called PP1. So you are welcome to call it PP1 instead of phosphoprotein phosphatase, because that's a lot to say. That's a 1, not an I. Okay. So that brings us to our allosteric effectors. Which allosteric effectors help increase the activity of glycogen phosphorylase? So let's look at our slide. So we know our active form is on the bottom in green. Our inactive form is on the top in red. What on this picture is an allosteric effector that helps shift towards the more active form? Yeah, AMP, exactly. So AMP helps shift this equilibrium towards the active form. And you'll notice that AMP mostly acts on phosphorylase B, which is dephosphorylated. So normally phosphorylase B wants to shift towards the inactive form, but if there's a lot of AMP around, even though phosphorylase B does not have the phosphate groups on it, AMP will help shift it towards the R form anyway. So that's why there's sort of separate control covalently and allosterically. Yeah, so we have on the right, we have phosphorylase A. Phosphorylase A is phosphorylated. Generally, that's going to make it want to shift more towards this active form. Phosphorylase B is dephosphorylated. That's generally going to make it want to shift more towards this inactive form. But there are also allosteric effectors that will act on each of these different forms and shift them towards one form or the other. So for phosphorylase B, even though it's dephosphorylated, if there's a lot of AMP present, it'll shift the equilibrium down this way, back towards the active form. Yeah. And this also, let's talk about that after we talk about the rest of the allosteric effectors. So, which allosteric effectors will help decrease the activity of glycogen phosphorylase? Yeah. Yeah, ATP is one of them. Who has another one? Yeah. Yeah, G6P. And G6P is glucose 6-phosphate, in case anyone was not sure. And those both act on the phosphorylase B. Which allosteric effector acts on phosphorylase A? Yeah, glucose. And so I think now is also a good time to sort of review why do those allosteric effectors do what they do? So who cares if there's a lot of AMP or ATP or glucose in a cell? Well, your glycogen phosphorylase cares, right? So basically, what is glycogen phosphorylase doing? It's breaking down glycogen into glucose monomers, and that way we can use that glucose to make ATP, to use as energy for the cell when it needs more energy currency. So if there's a lot of AMP around in the cell, that means the cell is in a relatively low energy state. It's used up a lot of the ATP, more of it is in the form of AMP. So that's a sign that, hey, we need to start breaking down more glucose to make more energy. So that's why AMP is going to help shift to the active form, because we need to start breaking down glycogen to free up more glucose. On the other hand, if there's a high energy state in the cell, if there's already a lot of ATP around, we don't need to break down more glucose to make more ATP. There's already plenty of ATP. So this is going to turn glycogen phosphorylase off or make it more inactive. And glucose 6-phosphate, the same thing. Glucose 6-phosphate is one of the intermediates in glycolysis that we're going to learn about in chapter 15. Glucose 6-phosphate, if there's a lot of it, that means there's already plenty of glucose being shuttled into glycolysis to be made into ATP. We don't need to free up more glucose to make more of it because there's already plenty of it available. So again, we don't need glycogen phosphorylase to break off glucose molecules from glycogen. And then glucose, same thing for phosphorylase A. So if there's already plenty of glucose in the cell, there's no need to free up more glucose from glycogen. So phosphorylase A can be inactivated if there's a lot of glucose around. So hopefully that will help you sort of understand what these do, so you're not just sort of memorizing a list of effectors and whether they activate or inactivate. It can be really helpful to think about what's actually going on in the cell in terms of what the cell needs or doesn't need, and that will help you understand why they do what they do. And so you don't need to just sort of try to memorize a big long list, because we're going to be talking about a lot of different enzymes that are going to get controlled by a lot of these similar sorts of factors for the same sorts of reasons, whether the cell has high or low energy levels, and whether there's a high or low nutrient level, especially of glucose, within the cell. So that brings us to our last part of our table, the R form and the T form. So is the R form for increased or decreased activity? Yeah, it's increased. And what about the T form? Decreased. So all of these types of factors are going to be coming up again as we talk more about glucose metabolism for the rest of the semester. So I encourage you to start thinking about how energy levels are going to affect what enzymes need to do or need to not do. Any questions about glycogen phosphorylase so far? Yeah. had said what? I'm sorry. Glycogen phosphate. So, yeah, glycogen phosphate is not an enzyme. Yeah. So, yeah, and you can find that information also on this chart. So we have phosphorylase kinase. This is going to catalyze a reaction of adding phosphate groups onto the phosphorylase enzyme using ATP as a source of phosphate. And then we also have phosphoprotein phosphatase that does the opposite. It uses a hydrolysis reaction to break off those phosphate groups as free inorganic phosphate to make more of this form. And this is also called BP1. Any other questions? All right. So let's now think more about enzyme activity and allosteric effectors. So here is a graph depicting basically a Michaelis-Menten curve, right? We have reaction rate over here. We have substrate concentration on the x-axis. So the blue curve, which is the middle curve here. I know last time we had trouble with colors. This is the blue one. You can see them this time, right? Okay. So the blue curve in the middle is representing catalysis by glycogen phosphorylase without any allosteric effectors present. This is sort of its like base catalysis rate based on just levels of substrate. And then there are two other curves, a green one and a red one. So take a moment and think about which curve represents catalysis in the presence of our three allosteric effectors. And so to help think about this, think about for these allosteric effectors, what are they going to do? Are they going to promote the R form or the T form, which is more active or more inactive? And what would that do to the curve? Is it going to shift left or right? So I'll let you take a few moments to think about that. Okay, so let's just think about the curve. So what is our green curve representing? Increased activity or decreased activity? What's that? Yeah, so our green curve is increased activity. So we are more in the R form. So this means, so basically you need less of the substrate concentration present to get to like the same reaction rate. So if you look at this dashed line that represents 1/2 Vmax, to get to 1/2 Vmax, you need a lot less substrate for our green curve compared to our blue curve, right? So it's more active. Which also means our red curve is showing us decreased activity, right? So it's shifted more towards the T form. And for similar reasons. So if you look at that 1/2 Vmax reaction rate, you need a lot more substrate compared to the blue curve to get to that same reaction rate. So it's a less active enzyme. You need to sort of force more substrate into it before it gets up to this arbitrary middle reaction rate. So now that we know which curve is which allosteric effector is for which curve? Yeah. Yeah, yep. Change back to green. So AMP is the green curve. And what about our red curve? Yeah. And yeah, I think one other last thing I wanted to say about this is this curve has a sigmoid shape, right? It's not just plain hyperbolic. So this is going to show us that there's some cooperativity happening here. And the cooperativity that we see is because there are two possible phosphate groups that can be added onto glycogen phosphorylase. So if you look in our last picture, two phosphate groups. And so there's cooperativity for addition of those phosphate groups. If one is added, the second one is more likely to be added. And so that's where this S shape sort of comes from, because of the cooperativity of those binding sites for phosphate. Are there any other questions about glycogen phosphorylase? All right. So this is what I have for chapter 12. So I'll give you all maybe a 3-minute break, and then we'll move on to chapter 13.